Good.
Great. Um, and now our last presentation for this session, but hopefully one everyone has been looking forward to, is by Jeff Andrews and Mark Grossman at Microsoft. And they will be talking about the Xbox Series X architecture. Jeff's a distinguished engineer at Microsoft, where he leads the Silicon IP architecture in the Azure Silicon Engineering and Solutions organization. And he's had a key role in Xbox architecture since the development of the first Xbox began about 20 years ago, I think. Mark is a principal architect and has been responsible for the Xbox GPUs since the first the first of the Xbox One series. And prior to Microsoft, Mark was a co-founder of Silicon Graphics, and he's also worked at Evans and Sutherland, ATI, and AMD. So please welcome Jeff to begin the presentation.
Thank you, John. Hello, thank you for attending our session discussing innovations and motivations behind the Xbox Series X silicon architecture. I'll be covering system level, SoC level, and new Microsoft IP. Mark will follow with more details about the new Microsoft GPU innovations. I'd like to call out 3 attributions. First, thanks to our session chair, John Sell, who worked with us at Microsoft for 14 years as SoC architect lead on Xbox SoCs and is now at Intel focusing on security. I'd like to thank John for his tireless efforts on the Xbox Series X SoC, which he was great helping. Next, I'd like to thank the many hundreds of people within Microsoft, AMD, and TSMC who are directly responsible for the Xbox Series X silicon, enabling the hardware and software for the console experience. Lastly, I wanted to thank Phil Spencer and Xbox management that have enabled a tech innovation-driven approach to Xbox that put game developers first, enabling renewed Microsoft leadership in direct 3D software and hardware in our silicon teams. This is empowering game developers to get technology out of the way and to deliver their vision to gamers worldwide. Okay. Here's a list on the next slide of key silicon hardware innovations in Xbox Series X that we have time to mention today. The first column is about CPU, GPU, and DRAM subsystem. I'd like to highlight our Zen 2 server class CPU cores, which we're really excited to bring to consoles. Hitting 120 hertz and ever larger living, breathing worlds required a transition from mid-range CPUs that we had the last couple generations to the best high-end out-of-order CPU cores. Next, the green items in the GPU, which is the heart of the silicon and system, will be covered by Mark Grossman, our lead silicon graphics architect. The next column is about hardware accelerators. The Xbox Velocity architecture is all about enabling game engine developers the least amount of compromises to harness a large multiplier on their use of DRAM, leveraging the performance of NVMe SSD drives. Next, we have audio hardware engines enabling project acoustics and other audio processing. These engines are tailored for audio math. They provide reserved performance for audio designers to enable a huge uplift in audio experiences without conflicts with graphics and other workloads in the system. I'll cover display a bit later. Lastly, we're going to mention some hardware innovations in Xbox hardware security, which has been significant starting with Xbox 360, but we nearly never discuss it publicly. The next slide shows a bit about the physical aspects of the chip. The Xbox Series X SoC is in TSMC N7 enhanced and has more than 15 billion transistors and is a 360 millimeter squared die. I wanted to first point out the 2 CPU clusters of 4 cores each that are in the upper, in orange, on hopefully your monitor as well, in the upper right and left. Next, please notice the GPU is basically consuming most of the die area of the chip, especially when you consider the full extent of the GPU. The amount of die area going to the GDDR6 PHYs on the periphery, out here you see all of them, and then the SoC fabric coherency and GDDR6 memory controllers is effectively mostly for the GPU. A non-GPU system would have far fewer channels and far less bandwidth. And so nearly all of that die area is GPU. As a result, you can understand that our graphics technical fellow graphics team and game engine developers are exceedingly happy with giving as much diary as possible to the GPU, which they always love. Lastly, the other hardware engines are up here in the notch between the two CPU clusters, and we'll talk about them later. I'm just going to spend the next couple slides times on talking to this diagram and not going through the bullets. On the left of the diagram, we have the two Zen 2 clusters. There are 8 cores running at 3.8 gigahertz with 1 thread enabled, or 3.6 gigahertz with 2 thread enabled. One Xbox extension, hardware extension to Zen 2 is SP Leap, which is additional hardware to prevent escalation of privilege attacks. We had an earlier version of SP Leap in prior Xbox One systems, but needed to redesign in the Zen architecture to work in Zen 2. SP Leap stands for Security Privilege Level Execution and Access Protection. We also brought over the server desktop AMD CPU die Zen 2 2x floating point pipelines. When using AVX256, this gives a peak of 32 single precision floating point operations per clock cycle, or 972 gigaflops for the 8 CPU cores, which is nearly 1 teraflop. This, compared to prior generations, is a pretty crazy amount of the most common floating point used in game workloads. At the bottom of the diagram is the GDDR6 channels with 16 gigabytes of G6 on the board. There are 320 DQ pins total running at 14 gigabit per pin per second, which results in 560 gigabytes total bandwidth. Also, the huge number 320 DRAM banks allows for higher utilizable bandwidth and lower average CPU latency, despite the very high graphics bandwidth that's beating on the DRAM. At the top of the diagram are hardware accelerators, including display, video, and video codecs. We'll get into HSP, MSP, and the audio units in more detail later. Next, I wanted to speak to the many new features in the hardware display processing. Display processing is the most difficult real-time engine due to large bandwidth for all display planes. It's very important to keep nearly all display processing off of the GPU's unified shader engine so more GPU perf is available for rendering. The Xbox Series X adds full linear light processing, enabling extremely high-quality display processing, including resizing composition between our input display planes, 2 of which are used by the game engine. In the early days of high dynamic range and wide color gamut content, there were often compromises made, which meant some operations were done on gamma-coded pixel values. The Xbox Series X completes upgrades of all the needed processing steps to enable math to operate on linear light values and not nonlinear gamma-coded light values. This, in addition of a hardware 3D LUT, removes compromises and even more workload off of the GPU. Finally, I'd also like to quickly mention 3 features our team had been trying to bring to HDMI standardization since the beginning of the HDMI 2.0 efforts, and now are fully implemented in HDMI 2.1. We're very happy to see these after so many years of effort. First one is ALLM, Auto Low Latency Mode, which enables console and displays to automatically pick the best low latency mode without user involvement. Next, VRR, Variable Rate Refresh, is a cross-company based standard for enabling lowest latency between render and the photons emitted from the display. And third, DSC, Display Stream Compression, brought to HDMI for the first time in HDMI 2.1, enables 8K P60 pixels to have full chroma resolution instead of 420 or 422. As mentioned before, Mark will cover the GPU in more detail. I'm going to skip slide 7. You can see these in the uploaded, which was it was about Moore's Law, and that's been covered quite a bit. The main takeaway for that was the increased overall die cost for roughly the same die area new process nodes, and you can see that in the table in the lower left. We basically have the same die area across 3 different technologies, and it's significantly more expensive for the die in the newest one in N7. This works well as long as the additional hardware is efficient and there's software composable workloads. Okay, next. Now to have a look at our Microsoft-created hardware engines. First, the audio engines. Overall, the 3 hardware audio engines in the Xbox Series X have more peak hardware single precision floating point than all the 8 cores in the Xbox One X, where the CPUs ran at 2.3 gigahertz. The CFPU2 is a new hardware engine focused on efficient audio convolution, FFTs, reverb, and complex math that audio commonly uses. An example of the uses of these in complex algorithms is Project Acoustics, which is a Microsoft effort to model environments, and 3D audio sources are simulated real time to produce audio sounding like real physical environments. For example, you could project these 3D sounds into an environment that sounds like you're in an aircraft hangar, cave, symphony hall, or an echoey locker room with lots of occlusion. Next, MOVAD is a hyper real-time Opus hardware audio decoder with throughput matched high-quality sample rate converter. It can do greater than 300 real-time channels of Opus. Opus was the most optimal quality compression trade-off audio codec that we could find, so that's what we made into hardware. Opus is more optimal as it has Silk voice codec and Celt music codec and can do hybrid variations in between per audio frame. The SRC hardware engine in MOVAD has greater than 100 dB signal noise ratio quality across game usage cases, which are much more difficult and varied than traditional music and voice audio. Simpler typical audio usages results in greater than 138 dB SNR, which is very high quality territory. The Logan engine, which was in Xbox One SoCs, is still providing lower level, more common audio processing offload. To save time, I'll quickly mention two things about HSP Pluton and MSP. The HSP continues Xbox hardware security innovations with SHAC, which stands for Secure Hardware Crypto Keys, and orchestrates security operations without software firmware involvement. The MSP does hardware accelerated offload of high bandwidth streams of storage data to and from the NVMe SSD. Performing these workloads properly takes a great deal of CPU, but we can save the CPUs for more game engine processing, reflected in better games rather than spending CPUs on repetitive crypto hash and compression. All right, this slide sort of describes the motivation for the Xbox Velocity architecture. The biggest thing is DRAM has had problems shrinking the capacitor now for many years. This started around 2008, 9, we were getting very worried about this. Fortunately, Flash in exchange has continued to cost reduce very well, and this enables subsuming the hard drive, which resulted in many NAND flash chip instances to deliver the needed bandwidth for refilling the DRAM cache. The other awesome value to users is that hard drives are doomed to have increasingly poorer load times. This is due to the inherent square term density versus linear bitrate problem. This is fixed with the NVMe SSD and the hardware software acceleration of storage. Sampler feedback streaming is a GPU innovation that Mark will go into more detail about how it actually works. But I wanted to quickly go through the high level and the effect at the SoC system level. First, basic background. SFS breaks into three pieces of function. First, the GPU has new hardware to directly emit metadata that records active texture portions. For example, the portions that want to be in the DRAM cache. The game developer then controls and prioritizes what to bring in and to free. Direct storage is a new API and drivers that takes it from there and manages the SSD, the MSP, relieving the game developer from having to deal with that complex orchestration and performance optimization. Going just a bit into why this works to deliver 2.5x game art DRAM working set effective capacity. Look at the render in the upper left. This has false coloring over the rendering to show which texture level detailed map is covering which portion of each object in the scene. The red is the most detailed map. The most detailed map in a MIP chain takes 75% of texture storage due to the 1/16 pyramidal MIP map chains GPUs use. You can see the texture MIP chain for the active texture coverage in the lower left. In that rectangle with the different pieces, you can see the black area savings portion surrounding the red. This is the savings ratio, which we get to multiply times the texture, 75% of texture space for the most detailed maps. There are also savings in the next map down, but as one expect, there is more active coverage in the coarser maps, but conversely, these get so much smaller that any savings becomes a tiny consideration. This basically leads to how we can achieve the 2.5x game art capacity using the smaller amount of DRAM. Thanks for listening. I hope this gave some insights to a small sample of the new hardware silicon innovations in Xbox Series X. I'll now hand it off to Mark Grossman to discuss the Xbox Series X GPU and its key new hardware innovations. Thank you.
Hi there. The goal for the GPU was to create a console-class design that significantly advances gamers' sense of immersion in realistic worlds, or as our VP of Game Studios says, get the tech out of the way. Naturally, we had to increase the raw ops per second, but because of the cost constraint Jeff mentioned, we couldn't devote a lot of real estate to brand new functions, so we added enhancements carefully. This shows the overall RDNA-based GPU structure. It fully supports Direct 3D 12, feature level 12.2 in hardware. There are 4 shader arrays, each with 6 or 7 dual CUs for 26 total active. Each shader array has its own color, depth, rasterization, and primitive assembly units. A single unified geometry engine handles primitives, including mesh shading, and generates higher order surfaces. A new 3-level cache hierarchy optimizes data latency and sharing. It can directly snoop the CPU caches. All of this is fed by a dual stream, multi-core command processor with custom firmware. This is the workhorse of the GPU. It's the dual compute unit. It has 4 32-wide SIMD units, arranged to allow either 32 or 64 wide scalar thread groups and to allow sharing of local data. Each ALU lane does a fused multiply add per clock, performing full rate 32-bit math and double rate 16-bit math. The faster single cycle instruction issue rate reduces stalls. The sequencer co-issues up to 7 instructions of 4 types per cycle per CU, or 14 total for the dual unit. Architecturally, these CUs have 25% better performance per clock on average graphics workloads relative to the GCN generation. Let's look at the evolution of GPU capability since Xbox One. The normalized graph shows that process and design advances have allowed raw shader teraflops to increase 9x. That's great. It enables some stunning visual techniques. Now note that memory space and bandwidth have grown much more slowly, only 2 to 3x. Now note the brown line. I'll highlight it here on the graph. The number of TV screen pixels that have to be filled has gone up almost as fast as shader power. If you average out GPU compute and memory capability, the usable performance increase is somewhere in the 4 to 6 range, depending on the title. But we want much nicer, more realistic pixels. So how do we fill more better pixels and not blow the power budget? And the answer is architectural innovation. One important new feature is VRS, variable rate shading. Traditionally, we had to run a shader thread on every pixel or multi-sample to generate a color value. But for most things, that's overkill because you just don't have high frequency color variation everywhere, as the image here on the right shows. On average, you really only need to shade every other pixel. But if you did that everywhere, you'd lose details in some places. VRS addresses this challenge, allowing screen fragments to cover up to 4 pixels at a time using a set of bias controls. The rate can be determined based on knowing which objects have high detail, which primitives within objects, or based on individual 8x8 pixel screen tiles. For instance, the title knows best which areas of the screen will be blurred in the post-processing stage. A programmable combination of those rates is supported, and that increases or decreases the rate, the final rate, up to the global anti-aliasing amount chosen. Edge detail is preserved, and VRS can be used alongside other resolution enhancing techniques, including temporal AA, super resolution, and even checkerboarding. The actual amount of dedicated hardware for this is tiny, but can have a big payoff, allowing higher frame rates and more math per pixel. Another key addition is sampler feedback streaming, as Jeff mentioned. Previously, implementing partially resident textures depended on issuing soft page faults, where every sample instruction returned feedback that shader code had to react to, for instance, by recording the miss in an array. Also, validating new texture pages could mean a round trip through the host memory manager, resulting in significant delays or visual glitches. In Series X, we've added 2 new structures in hardware to assist with tile-by-tile management of a modest-sized working set of in-RAM textures. There's a residency map per texture that clamps the level of detail of each tile, and a request map that records the finest bitmap level that was requested for each tile since it was last reset. Tile size is flexible. Here's a drill down on the steps. This picture here shows a textured plane, the top one using LED 0, which is the largest, most detailed map, and the other bitmap levels below that, each a quarter of the size of the one above. The first step is to allocate virtual memory space for the entire texture, and that's pretty cheap and fast. Then we load all of the coarsest bitmap levels, here up to a quarter by a quarter resolution, and validate those pages. For example, a 1K by 1K texture needs 1.3 million pixels virtually. The coarse levels require just 87,000 pixels to be resident, which is like 6.7%. Next step is to render. Imagine the player is you viewing the slide. The front edge of that slab is closer, therefore requires more detail. The shader executes a single macro sample instruction that combines lookup of the current detail level and the fetch of the actual texture. Here, the texture LED is clamped to 2 everywhere to start with, even if higher detail would have been better. Next, since the shader has already calculated which finer LED tiles should have been fetched, those values are captured in the separate recording map. Here, the closer tiles in green needed more detail. The farther tiles in red needed less than what was resident. The latter are candidates for eviction if the cache is full. Next, after rendering, the application reads back the record, compares with the current residency map, and brings in the needed higher detail tiles from Flash. Note that where an LED 0 tile is needed, the corresponding region of LED 1 is also loaded to provide the right detail everywhere in that region. Finally, the updated residency map is uploaded to the texture unit, and the next frame is rendered with the finer detail ready to use. And there's a second mode of the recording map that tracks access of each tile of each LED to enable texture space shading on demand. We'd like these new tile maps to stay on die for low latency access, so they should be as small as possible, ideally 1 pixel per tile. We also want smooth transitions between the tiles. Traditional texture bilinear interpolation sampling on a coarse map gives you wrong results because in the transition zone, you get a finer LED clamp value where that LED isn't resident. For example, the red tile leaking over the boundary in the left picture. So with our smarter filter function, the transition zones are moved inside the coarser LED texel, so this artifact is completely avoided. And overall, with a very small incremental hardware cost, SFS gives the same or better level of visual detail with a lot lower latency and a lot lower memory cost. We do support DirectX ray tracing acceleration for the ultimate in realism. But in this generation, developers still want to use traditional rendering techniques evolved over decades without a performance penalty. They can apply ray tracing selectively where materials and environments demand. So we wanted a good balance of die resources dedicated to the 2 techniques. The images show an example of the visual benefit of ray tracing for Minecraft. We've added hardware embedded in the compute units to perform intersections of rays with acceleration structures that represent the scene geometry hierarchy. That's a sizable fraction of the specialized ray tracing workload. The rest can be performed with good quality and good real-time performance with the baseline, shader, and memory design. The overall ray tracing speedup varies a lot, but for this task, it can be up to 10 times the performance of a pure shader-based implementation. A few other architectural enhancements are notable. Game engines certainly can make use of machine learning inference for a variety of game-related tasks, from character behavior to super resolution. So we've added a small amount of extra logic to the compute units and get up to a 10x improvement in these tasks versus using standard shader apps. We also have 2 completely independent command streams supported from 2 virtual machines. The main title OS along with the system OS, with work gracefully interleaving on the rest of the GPU, along with work for multiple asynchronous compute queues. We also support a 32-bit high dynamic range color format for rendering and display, giving significant quality benefits compared with the 1110 RGB format, and space saving is versus using 4 FP16 values. So at this point, we would have liked to show a cool preview video, but sorry, we won't. Fortunately, you can find some nice ones out there on YouTube already. Meanwhile, please enjoy this awesome still image representing the kind of visuals you can expect from the next Xbox. So that's all we have. Thank you for playing.
Thank you, Jeff and Mark. And we have a lot of interest and a number of questions. And I'll let each of you guys decide which one you're going to, or which of you is going to answer them. Well, I think I know what the answer to the first one's going to be, but I'll ask it anyway. Is the TDP, I assume that the questioner's referring to power, of the Xbox Series X GPU the same as the Xbox One's GPU?
Yeah, I'll answer that. So we're not commenting on power consumption, and I'll give roughly the same answer I gave 15 years ago during the 360 at the end of the 360 talk. There's so many things that are involved in the TDP, and there's a huge number of trade-offs and validation and operations related things that we're not really able to describe it unless you describe all of it in a reasonable technical fashion. So we don't go into that, and it also relates to COGS, which we don't want to disclose. So, but thanks for asking. It's actually a good question. We just can't answer it.
Well, the next question is might be a little easier or more possible to answer. And I'm actually going to maybe change, well, the question, I'm going to change this question a little bit. The question was, is there a way to bypass the GPU's cache? And the way the question was asked, it was, and write to the CPU's cache. But I think the way that I'd like to maybe ask for you to comment on is there a way to bypass the GPU's cache and stream data directly to or from memory? And if you want to comment on how that interacts with the CPU cache, please do.
Let's send that to Mark. You should answer that. Mark?
It's really hard to hear. Sorry, I can't hear Jeff at all. So there's a whole bunch of cache modes, programmable for the GPU caches. Too many to mention, but there's standard LRU. There's some like streaming modes, some bypass modes. You can mark things as coherent or not. So probably in there's what this questioner wants.
Well, I think one of the possible questions related to that I'll ask then is, what about coherency between the GPU data and CPU data and CPU caches?
Can snoop the CPU. That the reverse requires software intervention.
Okay, next. Question that I'm going to field to you is, are you happy with the DirectX 12 as a low overhead API? Do you have a lower overhead API that's closer to the hardware?
DirectX 12 is, there's a lot of it that is left to the user, like lots more of the memory management aspects. There's some Xbox specific enhancements that the power developers can use. But overall, we try to have consistency between the Xbox implementation of titles and PC. So having a lot of divergence is not good. But I think overall, we work with developers extensively in the early stages of architecture to make sure that their highest priority needs are met. So haven't heard too many complaints so far. But then I'm a silicon guy, so maybe they just haven't dialed me up yet.
I'd like to add something to that, John.
Go ahead.
So this has been said before in Xbox, and this has been true since the original Xbox. We have a smash driver model that takes the HAL and the runtime layer and smashes it together. And the games on the game binary implement the hardware laid out data that the hardware GPU eats directly. So it's not a HAL layer abstraction, and it makes it significantly more efficient. Microsoft also pretty much rewrite, so basically we completely rewrite the driver, smash it together, and this is Andrew Goosson's team in Sigma, which does a fantastic job on this, and replaces that and pretty much all the firmware in the GPU with Microsoft written firmware. And so it's significantly more efficient than in the PC.
So we've got several questions on the subject of clock frequencies. So I'll kind of lump them together into a couple of questions. One is there a linkage between the CPU and GPU clocks, or are they independent of each other?
They're independent. I mean, the hardware is independent. There's policy things that are decided above the hardware.
And then a related question is the CPU 3.8 gigahertz clock a all-the-time clock, or is that a turbo frequency?
That's an all-the-time clock. There's been a lot of work in our team to have low dynamic range variation depending on the workload. So there's been a decent amount of work to ensure that. So game developers don't have to deal with, oh, I'm running through a certain code path with this dynamic data, and now I'm seeing lots of variation on my frame rate. That's difficult for game developers.
And next one, this will probably be for you too, Jeff. Is the TSMC 7 nanometer that's used, is it the same as N7P, N7 Plus, or is it some unique flavor of 7 nanometer?
Yeah, that's a good question. TSMC would know the comparative better than me. It's definitely like, from Apple 2.5 years ago started production in N7. It's definitely the progressed over time, and a lot of production engineering and improvements to get the ion currents up and basically hit the performance targets we required for the CPU. There was a lot of work between AMD and TSMC to hit what we needed to have an AMD CPU be what we needed and wanted to have for an out-of-order CPU core.
And next question, probably also for you. In your presentation, you've said that the Zen 2 CPUs are server class, but it seems like the cache sizes are more of a mobile class. Do you have any comment on
the
that?
L3s are different. The problem is I can't say too much because I might say things that are AMD confidential. So I hesitate to go beyond that.
Well, so let's quickly go on to a couple more questions, because we have run over, but we're also the last presentation today. So unless the production team will start getting mad at us, but we'll squeeze in a couple more. First, with 20 channels of GDR6, is that really cheaper? I'm paraphrasing it a little bit, but is that really cheaper than 2 stacks of HBM?
So, just to be clear, we're not religious about which, DRAM technology to use. We needed the GPU to have a ton of bandwidth, and for us to be able to have lots of channels and memory banks, to have independent channels, so we have lower latency for the CPUs to sneak in and get their reads serviced. So if there was any hope of HBM being cheaper, there was actually HBM-LC that was being considered a while back, and basically different customers voted with their feet based on seeing the prices for HBM, and that was dropped in JEDEC. So anyway, I mean, it's really about what HBM costs, and it would just cost too much, frankly. And we can get the bandwidth. We absolutely can get the bandwidth we need out of GDR6. So that was the right solution.
So a related question on the die diagram, why are there doubled up GDR6 PHYs on the left and right instead of having some of them on the bottom of edge?
Oh, the bottom it's about the power delivery and the way the board interfaces to the chip. The GPU, as you can see, is rather massive, and so it has really high EDC and current requirements, and you need to have relatively clean copper to not be all Swiss cheesed up so that it has like problems with delivery of the current to the GPU and to the package. So when you have that much current coming in, you have to leave quite a bit of space unless you're going to go to incredibly fancy, expensive packaging. So the way that we did it is relatively common and a pretty cost-efficient way to do it.
So here's one that I think is a bit of should be a softball for game programmers, but it's what are the applications that need so much math dedicated to, what are the applications that that need so much sound processing?
Yeah, so that I love this question because I love audio, and we have a lot of people really passionate about audio in Microsoft. So as soon as you get into 3D positional audio and you're simulating real-world spaces, and then there's a thing that MSR Asia did a few years ago that allows us to simulate real-world spaces, and that's being brought to Xbox. And it requires, I mean, if you have 300 or 400 or 500 audio 3D positional sounds, and then on top of that, if you want to do HRTFs, it's a huge amount of compute. It's a crazy amount of compute, and so, and especially if you start including occlusion and other things that really then make it sound like a real world space. I mean, I'm really looking forward to being in the living room and have it sound like you're in some cave and there's like fighting going on or whatever, or you're just wandering through on a platformer and it really sounds like this totally different world, and that's imprinted on what you hear in your room. That would be pretty awesome. We've been looking forward to that.
Well, we've already kept the staff here for about 10 minutes over, so I think we will wrap it up at this point. But again, thank you for attending Hot Chips today and for the GPU and gaming session. And thank our presenters. Thank all of our presenters during the session, but especially the last two that are here now.
Thank you, John.